Hello, everybody. Right, we're about to start this. Do apologise for the delay in the changeover. We're going to be discussing heat reuse and power industry infrastructure. How energy can energy-intensive industries can drive the renewable energy transition and encourage heat off-takers. I want the panel to introduce themselves very briefly before we get into the questions. So over to you, David. You'll start at the right-hand end. David.
Short introduction, right?
Yeah.
My name is David Gyulnazaryan, in short David G. I'm focused on data center heat reuse and decarbonization. I'm from Nice, south of France. That's in short.
I'm Ed Ansett from i3 Solutions Group. I'm the founder and chairman of that companies.
I'm Keith Maclean-Martin, technical director at Pili UK, part of a power solutions division, which encompasses UPS stabilisation, but also medium-speed gas engines and that power infrastructure.
Hi, I'm Simon Prichard of Mitsubishi Electric. I'm the other side, on the cooling and obviously heat pump side from Mitsubishi Electric, working with our factories all over the world on IT cooling applications with heat pumps or heat recovery.
And Rob Barth, Director at FoundDigital. We're an investment and advisory practice specializing in energy, cloud and internet infrastructures.
Okay, right. So we'll start off with getting to the possible drivers. What does drive our data center facilities to want to actually provide reusable heat or power into the grid to make that possible? Is it altruism, philanthropy, leveraging to get your facility planning put through, or is it the permissions? Planning permission, or is it just really good business practice? And I'll start with you, Ed.
I think the truthful answer to that is there's an unmistakable appetite, public appetite, to see all industry globally improve and reduce its carbon footprint and become better environmental citizens. And I think that's the ultimate driver, and there isn't really any industry that can escape that. So it isn't really a question of altruism. It is more that it's driven by government mandate. It's also driven by corporate mandate, ultimately, in my opinion.
Okay, excellent. And Simon, if I can just put that question across to yourself, I think that the good business practice and the need as Ed put to reduce our carbon footprint wasn't originally there at the start. I mean, I think it needed a few drivers to get that going, and probably came from the investors first of all, needing to please their backers to get that money into the data center industry, which of course now we've dropped it. So, do you think there's another spin on this?
Well, obviously working for a manufacturer at the moment, obviously we supply not just to the data center industry, but to offices as well. And obviously we're seeing every single project we get involved with now, we have to give embodied carbon calculations for our products. And obviously then it goes into the operational carbon as well. So I think obviously there was a massive driver in the whole of the kind of built environment, shall we say, to drive carbon out of the industry.
Right, okay. So I mean, there's driving the carbon out of the industry, obviously from the perspective of usage and scope 3, but also you've got the embedded carbon situation as well. So when we're making products to make these projects possible, we're also adding to the embedded carbon very often that we're trying to exclude.
Yeah, exactly that.
Yeah, exactly, right, excellent. So if I could just get perhaps Keith, your view on how we're going to promote this?
In terms of the embodied carbon and the drivers in the industry, I think transitioning to energy security with enabling low carbon sources or carbon zero or net zero transition with generation sources of power, energy. We were just talking about it just in the previous session about renewable energy or carbon zero sources. It's a driver that we can't avoid in this industry, and being such a high power user, we have to find transitions to support the networks, to support the grid and the ongoing operations of the data centers. So I think it's a necessary driver that we're facing, that we have to find ways to do this. And technologies that we embed within that are absolutely accountable to deliver those carbon reductions.
Okay, so question now for Rob Barth. So in say Sweden, you've got organisations like Fortum who are own heating grids. In this country, I've just learned today actually that we have something like 11,000, you know, of these grids using reusable heat, which was news to me. I didn't think we had many at all. But I mean, how do we make this happen? Between it's not just a case of, oh, I'm going to build a data centre. I've got some waste heat. Do you want to use it? So how do we actually go out and find these projects? It's more than one person involved in this, but to actually find a project and work together and collaborate, where do we start?
Well, you're asking an electrical power engineer to opine on.
All right. Well,
let's
revamp the question.
No, enough to be dangerous.
We can put it to.
I'm happy to.
We can put it to the grid.
I just wanted to preface my remarks with that, and then we'll get
we
into.
could put it to the grid. How do you go about? So I've got some UPS, and I want to put it into the grid. I'm not paying for it.
Well, no, but I think those are two separate questions. One is dispatch onto grid as it relates to power and or energy storage or otherwise. The other related to, I think, your earlier question on heat. And I think on the heat question, I mean, it's maybe twofold. One is a question of adjacency. So where does the heat sit relative to a potential point of offtake? And secondarily, what's the grade of that heat? Most of the data center heat rejection we're talking about today is low grade and is not good for man nor beast in relation to where the data center sits and the potential off-taker. And to try and address that retrospectively, i.e. there's not been any forethought related to where this sits and how am I doing the onward distribution, how am I upgrading the quality of that heat? Because, for example, if you wanted to use heat to create coolth, in the case of an absorption chiller, and there are others on the panel that will probably get the numbers better than myself, but let's say 80, 90 degrees, we're getting 35, 40 degrees in terms of the rejection. But it also, I think, to a large degree depends, because if we're dealing with adjacency of turbines or engines, I mean, a turbine, you can take 200 degrees off some of the turbines, and if you're creating these data centers with physical adjacency to a turbine, irrespective of what fuel is powering that, there's definitely heat offtake opportunity there. I think on the secondary points, and maybe Keith is better placed to speak to this, but how we look at the electrical infrastructure building blocks of systems in terms of dispatch and supporting grid stability or short-term bridging opportunities, that's a secondary question, and I mean, may have an allied influence on how we think about the heat, but I think those are, you need to pass those two elements.
Okay, so I think, you know, we're at a stage where, you know, you're talking about the heat not being enough to be of much use, the waste heat. But I think, is it Simon who's on the heat pump side, or was that Keith?
Yeah, no, we obviously, the company you mentioned, obviously in Scandinavia, we've done several large projects with them now to upgrade the heat.
Yeah.
Using obviously a water source heat pump, taking heat anywhere from an old data centre where we had chilled water at 12 degrees and upgrading that to 60.
Yeah.
And then obviously basically Fortnum obviously sold the cooling back to Ericsson, who run the data centre, and sold the heat to the district network that they ran. And basically it was on the return loop of a district heating system before a biomass power generation centre. So basically it came back into the data centre at 30, went out at 60, and then got boosted up to 85 degrees back into the heat network to the villages up the road with about 3,000 houses.
Right. And is that using one heat pump or is that a series?
No, that was a single source heat pump.
Because I believe you can get it up to around about 150 degrees with a series of heat pumps.
Yeah, with other refrigerants that, yes, you can get up to them kind of temperatures. Yeah, we're doing it quite regularly now for offices as well. It's quite a common thing now to obviously take a low-grade heat to boost it. Obviously, we talk about air-cooled systems, but obviously with liquid-cooled systems, that temperature...
Yeah,
will be
55, 60.
Which technically you could probably put straight back into a district.
Yeah, but I think the key question there is what part of that transport system was in situ, as in the district heating and cooling principles of that onward distribution systems already.
The district network was already in place. And basically, they sold the concept obviously to Ericsson to give them some free cooling if they could tap into their heat that was available, basically. So it was a business development manager that actually worked for Fortum that came up with the idea. We've now done, I think, 4 in Finland, and we've done 1 in Ireland as well.
Okay, so what I'd like to do is put over to David. Now, I believe, David, that your expertise lies within immersion cooling. And so how do we extract the heat from immersion cooling and put it into the system?
Before answering right to your question, I want to just touch 2 fundamental questions. If we need 20 degrees in living rooms, why we supply 100, 120 degrees hot water to the district heating loop? And another question is about the servers. If CPU temperature is 80, 90 degrees, why we should use cold water with temperature 15 degrees? So everything is about established things and how people used to do that. So all technologies exist, how to use high temperature of the water to cool down the servers and how to use low temperature to heat up the buildings. And only thing which we need is to match the low temperature for heating and high temperature for cooling. So when we talk about immersion cooling, we have a chance to use high-grade water to cool down the equipment. Actually, it's not, I don't like to cool down. I like to use the term of heat transfer, to transfer the heat from servers to the heat users. And the idea of immersion cooling that we take all the heat rejection from all components of the server equipment, IT equipment, to the liquid. And that make much easier the task of the heating. So when you look on that center design from point of view of heat reuse, you re-evaluate everything. And as a result, you decarbonize the data center because the density is higher, you need 10 times less space. It means 10 times less embodied carbon of the building. You need by 30% less energy infrastructure. It means that your diesel genset UPSs will be 30-40% cheaper. And the cooling system. Now you don't cool, you heat up. You don't need anymore to make heat rejection to the environment. You use that heat.
Perfect, thank you, David. So, Ed, so bear with me for this, because I'm not quite sure where this question is going myself yet. Right. Okay, so in the back of my mind, I've got this notion that we're putting together quite successfully these redistributed heat projects with some success. We're trying to promote them, and we know what the industry is like. It's full of innovation, our industry. and we are innovating to try and get our chips to be running much cooler, use much less energy. We're trying to get our cooling systems much more energy efficient. There's changes always happening. Will that, first question, part of the question is, will that actually change the design? How do we actually future-proof those designs when we're building data centres, with that bearing in mind the contracts that you're running with perhaps Fulton maybe, or another user of your waste heat?
Okay, multifaceted question, right?
Absolutely.
So this is actually, it's not, it truly is an interesting question, because we all know whether it's immersion cooling or some other form of close coupled cooling is coming.
Yeah.
It's been sat on the horizon. I've been researching it well over 10 years. And we're edging closer and closer, and we're seeing more and more adoption, but we're still not seeing wholesale widespread adoption. So if we look at the largest, or the large system, I'm not talking about the smaller systems. The elephant in the room in this, in my opinion, is these new AI data centers that are about to hit us.
Yep.
Which I think inevitably will be some form of liquid cooled. As I say, whether it's immersion or some other form of liquid, some other form of close coupled cooling. Our dilemma in designing these days is, a couple of projects come to mind. One of the projects, one of the largest one, has got its construction time from now to completion is 8 or 9 years.
Right.
And so the difficulty we have is, we know that close coupled cooling, immersion cooling is coming, and by then we can't say for certain, but it's almost inevitable that that'll be mainstream. But what do you do? What do you design for? And there is no easy answer to this. It's probably more the question is, how do you hedge? How do you hold back as long as you possibly can in terms of commitment before making that fundamental decision? Because yes, you can convert conventional cooling systems to an extent, adapt them to some form of, let's call it liquid cooling, but it's not the most efficient way of doing it. So it is a conundrum that we face, because at the moment, you know, we look at most of the stuff that we are either doing or about to do, it's almost all air-cooled. We recently had an inquiry for a large liquid-cooled system. Whether it will go ahead or not, I really don't know. So it's funny, we've moved from small-scale liquid-cooled, a few hundred kilowatts, a couple of megawatts. Now we're moving to very large, but quite when this is happening, I'm not absolutely sure. I got a feeling, and I'm sorry this isn't very qualified, I've got a feeling it's much sooner than later. I think it's much sooner than later, but hopefully not tomorrow, because I'll look a fool if it's tomorrow.
But I mean, wouldn't you say, Ed, that, sorry, just to sort of build on that idea of, I mean, the way I see it is, how far is the water traveling in the system? Because, I mean, if you're looking at a chilled water basis of design, which is certainly how many of these data, or these early data centers started out life, I acknowledge a pivot to air-cooled, direct or indirect for a period. I think it's moving back to a chilled water basis of design, but you have to ask yourselves, how far does the water part of that system extend in this? Does it go from a heat rejection source on the roof via distribution pipework to a fan wall unit? So the division line there sits at the data hall level. Does it travel via a manifold to a rack? Does it travel to the chip? Or to David's point, is that a fully immersed bath that the servers and the chips are sitting in? And I think that's a key, because from an efficiency perspective, I mean, immersion makes a ton of sense on so many levels, but I think we also need to ask ourselves, I mean, the psychology of people is a key qualification of how this whole piece plays out. It's not a function of, is this a technically more sound solution than another? But what interests me, I don't see as much of the footprint compression opportunity as David alluded to. I see the two biggest drivers for immersion being the energy reduction, and from a sustainability perspective, the electrical cables, switchboards, generators, UPSs, all compressing as a consequence of your ratio of your peak to your IT demand being far better aligned in that context. But yeah, the spatial piece, I think the challenge is the geometry of these buildings. The heat rejection becomes the dictate of how much you can physically compress that building, particularly if it's sitting on the roof of the building. So I think those dry air coolers and that footprint of those DACs is probably going to say, okay, well, this is how much you can shrink this building.
Is that a question?
No, well, I'm saying I was very much supportive of David's first point. I just wanted to say on the second piece with the miniaturization or the opportunity to shrink this. Yes, how much you shrink the data hall, but then the overall building footprint, I'm not convinced.
Rob, you guys, you've got to remember something we often lose sight of. It's not for the first time in our industry we've talked about the improvement in efficiency. Now, in this case, the efficiency is predominantly around the energy overhead, the cooling. But every time there's been an inch of space available, the IT consumer network, in other words, the public, corporations have found very good reasons to fill it. So whilst I believe on the one hand I can see this shrinkage, I think in reality it won't happen. I think we're just going to consume more and more, and we're just going to apply more and more compute. So we'll never see it. It's a bit like, you know, applying the renewables to various grids internationally, and yet what's squashing that is the aggregated demand and overall electricity demand, if you see what I'm getting at. It's for me, it's analogous to that. We're going to use all of that space.
But maybe it's worthwhile for David to respond to.
Well, I will say that it will match. And the reason, because if we take air-cooled systems, we use dry coolers for low temperatures. And low temperatures is much harder to achieve than high temperatures. So when you have, let's say, 60 degrees water and you want to cool down that to 40 degrees and ambient air is 20 degrees, it is really easy to do. It is smaller surface of the dry cooler, and the same dry cooler which was for previous air-cooled system for 1 megawatt with immersion cooling can do 2-3 times more.
Yeah, so you're saying the frame size of your DAC is effectively allowing, because of the temperature.
Temperatures
Yeah.
is higher.
No, I do. I agree with that. But I think the broader question is, I mean, there's significant investment in technical real estate. So there were discussions earlier about life cycle associated with the different building blocks of system. We've got to come up with something intelligent that says to what degree do these older buildings, because the building's not going anywhere necessarily, get repurposed and that doesn't necessarily have to be aligned with a data center asset class or use case as a starting principle.
Yes, so what is the main obstacle in the market is absence of knowledge. So I think all of you heard about immersion cooling, about cold plates, about on-chip cooling. But how many of you know how to implement that? Only few people. Yes, maybe 3-5. So it means that the rest of the people still working with air cooling and still don't want to go out of this comfort zone. And that means that all these people need education. What we do, we create open source modular data center, which can be taken by anyone and evaluated and build it step by step. So Open Compute Project provide that opportunity. Anyone can take that design, evaluate that, adopt for himself, and learn how to do that. So this is the driver for the market, how to make transition from air cooling to liquid cooling and evaluate the savings. The calculation which we have made show that only on 1,000 servers we can save 1.2 million euros in 3 years. It's including NCAPEX and OPEX.
But what is your view on why these companies that are spending a disproportionate amount on R&D are not sandboxing or doing via proof of concepts larger implementations? I mean, certainly, yes, we're seeing one or two in the multi-megawatt space, but let's just say, why are these not traveling from a sandbox to a production environment with groups that recognize this? Because we can't possibly say they're not super intelligent leaders in these businesses that are not driving some part of this agenda.
There is an obvious answer on that. If you go to the colocation data centers and look for the customers, the reality that customers have low density racks, 5, 7 kilowatt racks, and this is because this is customer demand. We can not overall in the world drive and educate people, but if we go to the well-educated companies like cloud and etc., which have good IT directors, which looking for the high density and efficiency, they have requests in high density racks. And this is the driver, but this driver is not 100% of the market. It is growing. It is 5%, 10%. So when all the market will shift to that demand, then we will see that growth. But now we are talking about 5-10% of the market, which looking for the high density and efficient racks, efficient IT.
But to that point, if you've got a hyperscalers that currently, from a scale perspective, represent over 50% or more than that of total development on a self-perform, self-build basis, and these are the groups that are forward-thinking in that regard, why is there such a small percentage of this, let alone production environment? Why are you not seeing, and they trialing next generation implementations that are reflective of this principle? They still super creatures.
All hyperscalers work with liquid cooling, all of them. But each of them use own way.
I think the question is, I think coming back to this point, there's going to be a time when we will make that transition. It's just not clear quite when, okay? And I totally agree with David, that as far as I know, they've all got some form of liquid cooling production. Okay.
Yeah, I'm just saying it's not a statistically relevant sample base.
No, it's not, but it's like so many things in this industry, there has to be a period of time. You've got to think about it. I mean, why did we end up with a standard rack configuration? Just in terms of the physical rack, all right, we've got variants of that, but we eventually kind of ended up in a particular place with air-cooled servers, and we started with fault-tolerant power systems. We moved to quasi-fault-tolerant power systems. It's coming, Rob. The point is, I don't think any of us really know when it's going to become mainstream, and it's going to be a bit of a shock to the system, because if you look at traditional real estate, it will not be able to cope with it. It'll mean a whole load of new build. I do not believe you'll just be able to quickly flick the switch. Because the reason I say that is because I think, coupled with liquid cooling, the whole essence of that is the probably exponential increase in compute that will come along with it. I can't say that, so it's just based on what I've seen in the past, based on behavior patterns. We've never sat there and said, oh great, liquid cooling's come along, our compute requirements remain flat. They're going to go through the roof.
I want just to mark one thing, that we now more talking about data centers, but if we want to evaluate heat reuse, we should talk about heat users. It's been evaluate the drivers or obstacles which connected with heat reuse, with district heating or with end user. So what I want to say, that the driver for heat reuse is the energy crisis. The problem that many district heating companies have an issue with the price for gas, for fossil fuel, and they are looking for the new sources of the heat. And because some of the gas boiler houses don't have even access for the gas, in today conditions, and they are ready to pay for any cost of heat pump running just to have this low-grade heat. So, and another thing is about district heating. Not all the cities have district heating, and there is a challenge to connect 20 megawatts, 50 megawatts data center with decentralized buildings which don't have.
But it's not just district heating that uses waste heat. I think we have to, I know we first think of, these big grids going around domestic housing, but reused heat can be used, waste heat can be reused for something else. In Durban, they built a big data centre. The reason why they had it in Durban was evidently it's a port in South Africa, and being a port, they have to have the power 24/7. It's one of their regulations or stipulations, evidently. But they built data centre and the reused waste heat. They built greenhouses around it, which they grow crops from. So, and it was designed. It was almost like the smart cities, I suppose. It was designed into the whole thing. It wasn't just a thing that we'll reuse the waste heat and we'll build some greenhouses. So, I think we have to look at that, put that in perspective. There's other uses of waste heat. I just want to take this now to Keith, because it's on that thing. So should we go out and find projects? So what I wanted to go back to was something I've sort of lost track of. We used to talk about years ago about combined heat and power from generators. Now, if we could get our rotary UPS systems to work off hydrogen things and green fuels, is there a place back in society, in data center society, for CCPU or CHP and CCHP?
Absolutely. I mean, when you look at, we talk about the energy transition that we're facing right now. The grid can't be 100% renewable, can't produce all the energy that we need, and data centers have an opportunity to develop their own infrastructure, to support their own local operations, and integrating small microgrids. They can deliver their own local power needs, stable power needs for their own, and resiliency within that. But there's that opportunity to do the combined heat and power associated with those generation sources now as well. And if they operate as prime power generation, it's a constant grade of actually a really good quality usable heat that can be put back into, let's say, the local communities, whether it's through district heating, whether it's through other users in the local area. But that also offers the opportunity to not only support the heat reuse, it's also other power functions that they can do in the local area. They can provide resilient power to local communities or other users, symbiotic sort of energy providers and users in the area. They can work together and develop those flexible power systems to help work in that area and support not only their critical infrastructure, but the local networks as well.
Excellent. So we're a little bit out of time, but I just really wanted to throw that question across the board. Does anybody else want to come in on that?
On which one?
That one you've just been listening to here.
No, it was. We're working together. So.
All right. So basically, it was a double question, really. I suppose should we be thinking about CHP and the other things? Should we go out looking for projects and saying, throw in controversial terms, really, is what we're doing. Throw the low energy and the low heat use out of our data centers. Totally just make the heat, make the power, and go and find a project where we can reuse that for something else.
I think that has to be government policy led if you want that to happen. I mean, data centers predominantly choose their location. Where can I find the land? Where can I find the power? Connectivity seems to be much less of an issue these days. And then there's many examples of this. Okay, we're good citizens. We're part of CNDCP. How do I export my heat? Oh, there isn't anywhere to export it to because I'm nowhere near a residential community or so on. So,
but now if you are restricted on the locations of where to go to build the data centres by the power connections, if you build your own power generation sources, it gives you the flexibility to build them in different locations.
And therein is another panel right? Because, but that's the
Yeah,
whole-
but I think the infrastructure building blocks of what Keith does in a CHP context, in my mind, is very interesting because there's the heat reuse opportunity attached to the CHP. This is a really important thing from a power system perspective in terms of stabilization of grid. I mean, the national grid and all national grids has historically relied quite heavily on synchronizing torque and big inertia stores in the system. So the absence of that with the advent of a far greater degree of renewable variable penetration into the network is quite reliant. So I'm injecting kVARs back into the system, or I'm providing short-term stabilization services is super important. So you can be a good corporately, socially responsible citizen and also benefit, I think, both in terms of the heat and the
Yeah, but
power.
Rob, the problem with that in the past has been, one, initially was scale and then cost, okay? So this is one of the key things for everyone, you know, and ultimately it all comes back down to cost as well, right?
Yeah, but and customers' reticence in the early days for that. I mean, I've been involved in building very large DRUPS, diesel rotary UPS implementations over the years, and I can say with certainty the single biggest barrier to trying to say we want this to participate in any capacity on the grid was, well, no, we want this available to us, and I'm not interested in any discussion related to the grid. However, back to those imperative points, sometimes when there's no power, I mean, it alluded to connectivity. Formerly, connectivity as it related to availability zones or availability domains that these groups were building was super prescriptive. But when there's no power available, then I have to make an alternative plan. So now I'll go and look elsewhere, and I can stretch all of that. So all those foundation principles that say you have to do X or Y, and this is the maximum optical tolerance, just get thrown out of the window.
Yeah, I think there's also another case where some of the facilities in, I think it was Texas, can't quite remember, were putting load balancing the grid, basically, as you say. But they've given up. And the reason for it giving up, they're saying that it's actually costing them more to make the power. They're selling back at a cheaper rate. And so some of them actually said, we'll do
Yeah,
it.
but just to clarify, what I'm advocating is Keith and the data center owner, operator, developer, or the hyperscaler have implemented this. So this diesel rotary UPS system or CHP system is part of the conditioning form of infrastructure. It has the capability to do this, and obviously you want to embed that capability via G99 and like a UK context in what that does. But I'm not advocating for any additional infrastructure blocks. We're saying you're either going a static route of conditioning that power stream or a diesel rotary.
Not necessarily
not
diesel.
even
Well,
just
not even diesel rotary, but what I'm saying, the inertia store.
Yeah, exactly. I mean, but it can be inertia stores, it can be kinetic stores, it can be battery storage as well. It doesn't have to necessarily be restricted to just conventional diesel. We can adapt it to work with prime power generation with gas and blended hydrogen mixes, so giving you greater flexibility to adapt to the future needs of low carbon and zero carbon sources for generation, but also giving you the balancing mechanisms to deliver the stable power source that you need, while also providing complete uninterruptible power supply source, all essentially delivered in infrastructure that you're procuring already, but enhancing the functionality of it, and perhaps looking at it, instead of being a standby generation application, you move it to a prime power generation source, and you're actually using the assets that you're investing in already. It's delivering the reliability that you need in the locations, but it can enhance performance by delivering services to the grid while still protecting local assets at the time for the data center.
And sorry, Philip, the reason why I had the diesel hangover is courtesy of your comment on 24/7 serving in Durban, because they're absolutely doing that on diesel because Eskom is not delivering anything.
They can't even get the diesel right now.
I didn't say they was getting it out of the thin air, but yeah, you're quite right. Yeah. Excellent. Look, we have run over, which is a bit of a shame, really, because I think it's a really interesting panel. I think we've come up with some good subjects and or answers anyway, not to my poor questions. I'd like to really thank the panel, and before we go and get some lunch.